Okay, so hello everyone. So today we are proving that in a metric space, compact sets are closed and bounded. All right, so we have to see in a metric space why compact sets are closed and bounded. So let's try to give a proof. So let x comma d be a metric space and k be a compact subset of x. Okay, so we are in a situation where we have a metric space and we have a compact set. Now the first target, we first show that K is bounded. Okay, so how do we do that? So we know we can write K is union of all y such that y is in K, right? So that means I am taking K and I know that I can pick points in uh, y in K, and I can take the union of all points. I will get back K. Okay, and that is naturally contained in B of y comma 1 where y is in K. Right, so each point y I am going to surround with an open ball that is of radius 1. Now after this we have to use the fact that K is compact. So therefore I can say if I take C, which is B of y comma 1 such that y is in K, so this set will give me an open cover for K. Why this is open cover? Because it is containing all open set and it is covering K. So since it satisfies both the properties, we can say C is an open cover for K. Alright. But we know that K is compact, right? So but K is compact. So compactness means every open cover will have finite subcover. So this implies C has a finite subcover for K. That means I can find finite number of points. You can see that here there were infinitely many points. Now I can find a finite number of points which can cover K. That means there exists y1 up to yn is in K such that I can write my K as union of B of yi comma 1 where I is running from 1 to n. Alright, that means I have covered my K with finite balls. That means y1, y2, like that. There are n such balls which are enough to cover K. So that will mean that diameter of K is definitely equal to diameter of this union of balls yi comma 1, and that is nothing but, if I calculate union, that is nothing but if I have to just take summation of diameter of B of yi comma 1 where I is running from 1 to n, and each ball diameter is 2 because we have picked balls of radius 1, so that will be naturally less than or equal to 2n. That means K is bounded because its diameter is finite. Alright, now in the second part we want to show K is closed. Okay, so closed means it is enough to show that K complement is open. So what do we mean by open set? So we take any random x in K complement and we try to find r greater than 0 such that B of x comma r is contained in K complement. So that is our task. Okay, so now what we have done, we have taken any random x in K and we want to find an open ball surrounding that. So we know that K, I can again write it as union of y singleton y, where y is in K, right? And we know that x belongs to K complement. So this implies for each y, so we can easily visualize here. We have K and we have K complement, and here x is there, and here there are y's. All y's are here. Okay. So that means for each y, okay, so for each y, so we can see they are different. So that means by Hausdorff property, we know that if x and y are separate, we can surround them by disjoint open balls, right? So for each y, by Hausdorff property, so there exist Rx, Ry greater than 0 such that B of x, Rx intersection with B of y, Ry, that will become, so that will become empty set, right? Because the balls are disjoints. Now after this, again we have to make use of compactness of K, and we have got something like this. So this can help us to get an open cover for K. So therefore what I will write K is union of B of y, Ry, where y is in y. So again C, which is B of y, Ry, where y is in K, is an open cover for K. Okay, so the idea is pretty simple. Because of Hausdorff's property, we constructed a open cover for K, and now we know that K is compact. So but K is compact, so that means we can conclude there exists some ry1, ry2, ryn greater than 0 such that I can write my K as union of B of y, r by I, where I is by I, where I is running from 1 to n. Okay, so there will be finite finite subcovers. Okay, that means I just rewrite it. That means there exist finite y1 up to yn belong to K, and we have corresponding ry1, ryn, and rx1, rxn greater than 0 such that I can write my B of r by I can write K as a union of this subcover, sorry, I can write K as union of B of yi, ryi, I from 1 to n, and we already know that B of xi, B of x, so B of x, rx I intersection B of yi, ryi is empty. Okay, so what we have done, actually we had K complement, and here we have found y1, y2, like that some finite ryn, and we have x fixed. So we are just taking balls around x such that they are not intersecting the balls here. Okay, so what we will do, we will choose r, which is minimum of all rx1 up to rxn. Okay, so we will take the smallest ball so that it will not intersect with anyone. So that would imply B of x, r intersection with B of yi, ryi will be always empty, right? So but K is contained in this, right? That means B intersection with, if I take all union B of yi, ryi, that will be empty because of De Morgan's law, and that will mean B intersection with K is empty. That means B is contained in B is contained in K complement, where actual B is nothing but B of x, r. So therefore via this construction we can find some radius where B is contained in K complement. That means K complement is open, and that would imply K is closed. Okay, so the idea is very simple. We have to just pick any random point, say x in K complement. Okay, and we have to find a radius. So we just take some finite balls here, and accordingly we get balls here also, and we take the smallest ball. So that ball will be contained in K complement. So K complement will be closed. So therefore K will be open. Okay, thank you.